Hello and welcome to another very exciting See the Change USA webinar. My name is Vincent Weiss. I'm the Manager of Product and Training Development. And today we are going to start part 3 in a 4-part series where we are covering all of the topics found in Energy 1 in the See the Change USA curriculum. So without any further ado, let's get started. A few housekeeping items. So for this webinar, there will be no audio or video, so if you have your video turned on, if you could please shut that off now because you will not need it. So we're going to communicate using the chat box feature. To open up the chat box, if you don't see it on your screen, put the cursor at the top of your screen and then a drop-down menu will come down. Click on the ellipse at the far right and then you should see this chat. So click on that chat and then it'll open up the chat box. So if you have any questions or comments or anything, do feel free to ask those questions while I'm going through. And we're also going to have a question and answer session at the very end of the webinar for you to ask any questions at the end. All right, so this session will be recorded and this recording will be posted on both the Physics Lab and the See the Change USA Edmodo group. And the PowerPoint for this that I'm going to use for this webinar will be posted onto the See the Change USA Edmodo group. If you're not a member of that group, I will show you how you can become a member at the very end of the webinar. So the purpose, first and foremost, is to build your confidence in physics. You are all exceptional science teachers, but our aim is to help you to become world-class middle school physics teachers. And this all starts with being confident in a classroom, especially confident in the topic of physics. And it's also to help you to bring these high-level physics concepts to the middle school mind. So we are going to address a lot of common misconceptions, how you as a teacher can diagnose those common misconceptions, and how you can use different examples and different ways to pull them out of those common misconceptions. So who is it for? It's for teachers looking to take their students to a deeper level of understanding. We are going to get into some topics that go beyond what are just in the lessons on the physics lab, because we want you to know just a little bit more, and that way in the classroom you are able to help your students get to an even deeper level. And it's also for teachers who do not have an extensive background in physics but would like to master the concepts. Like I said, we go a little further than the lessons go, and that's on purpose. It's so you can always stay a step ahead of your students. And it's also for teachers looking for alternate ways to explain concepts to students. So throughout the webinar, we'll have different graphs and different pictures and different tools that you can use to explain these concepts to students. So what we'll cover the content specifically found in lessons 1.4.11 through 1.4.13. So these handful of lessons from Energy 1. We will look at the conservation of energy and discuss where kinetic energy comes from. And then we'll also look at the kinetic energy equation, discuss some of the non-linear features of kinetic energy. We've not seen any non-linear functions or nonlinear equations as of yet, but as it turns out, there's some pretty interesting and counterintuitive things that come out of kinetic energy. And then we'll discuss some simple transfers of energy in light of conservation of energy. We could see how potential energy and kinetic energy kind of transfer back and forth between each other. And then at the end, we're going to have a question and answer session about the content found in these specific lessons in Energy 1. So stick around for that. All right, so first off, kinetic energy. Kinetic energy is the energy of motion. If anything is moving, it has energy. And we just happen to call that energy kinetic energy. So there are two ways something can have kinetic energy. The first way is through linear motion. So if anything is moving in a straight line or just forward, if it's just moving from one place to another, then it has this linear motion. And we call this linear kinetic energy. So it's just energy that comes from linear motion. We can also have energy that comes from rotational motion. So you have something that's spinning, it has a certain amount of kinetic energy that we call rotational kinetic energy. So for our purposes, we are just going to focus specifically on linear motion. But just so you as a teacher are aware, there are two different types of kinetic energy. There's linear kinetic energy and there's rotational kinetic energy. So to keep this always in the forefront of your mind, because a lot of times in classrooms, we are rolling things down ramps and there is rotation involved. So just to keep in mind that though a thing speeds up, it also speeds up its rotation. And unless we can account for both linear and rotational, a lot of strange things happen. But unfortunately, we'll not get to talk about rotational, but we're going to talk about linear. All right, so whenever we come to energy, we need to remember energy cannot be created. It has to come from someplace else. We call this the conservation of energy. It's one of the most fundamental and one of the most important laws in all of physics. So if we have an electron, or an apple or the earth, doesn't matter what object it is, if we want this object to move so that it has kinetic energy, we need to feed it with some energy somewhere else in the universe, and then it will have kinetic energy and it will start to move. So let us take a look at this apple. If we want this apple to be able to move, we need to supply it with some type of energy. Like let's say we put it on the top of a really tall building. Now it has a specific type of energy. It has potential energy. And if we were to bring in a little meter that measures the potential energy, we see it's completely full, being on top of that building. But as it falls, that potential energy decreases, so that energy goes somewhere else. According to the conservation of energy, energy cannot be destroyed. It goes somewhere else. So if we reverse time and bring in another meter, where we measure kinetic energy, we immediately see that as the apple loses potential energy, it gains that kinetic energy. So in this case, we see that potential energy becomes kinetic energy, and this is what gives us the motion of the apple. So here we have this tree that has potential energy, and as it transforms into another type of energy, that's how we get kinetic energy. Or here we have a bucket, and inside this bucket is an explosive device that is really fueled by thermal energy. And it is that thermal energy that creates this kinetic energy after it blows, sends the bucket a mile high. Now, when it comes to kinetic energy, what's really nice about it is that it's easily measured. Unlike thermal energy and potential energy, these two types of energy are quite difficult to measure. Specifically, potential energy, you have to know the forces involved are acting on an object. And thermal energy, you need to know temperature, mass, specific heats, and it's always changing. So kinetic energy is really nice in that we only need to know two things to measure it. We need to know the mass of an object, and we need to know the velocity of the object. Pulling in all the things the students learn from basic motion, in principle, they can measure these two things. So a couple other features, we see that kinetic energy is equal to 1/2 mass multiplied by velocity multiplied by velocity. We see that there's only one mass and there are two velocities. We will see that kinetic energy is much more affected by changes in velocity than changes in mass. But the kinetic energy of an object is affected by both mass and velocity. So this is the longhand version. We can write it in a shorthand version by combining everything and simply saying kinetic energy is equal to 1/2 mv squared. And the units of kinetic energy are joules. So here is something kind of interesting. Notice this 2 right here. This 2 is, whenever we see some variable raised to the second power, it means that number, whatever it is, this happens to be velocity, gets multiplied by itself. When we come across these type of equations in physics, this is always a very exciting thing because this says that this equation is nonlinear in velocity. And nonlinear things are always really fun to work with because they show us that there are some really unintuitive things that we can draw out of them. So I want to talk a little bit about the relationship specifically between velocity and kinetic energy. So here we have these two buckets. On the left is velocity, on the right is kinetic energy. And if we just have a unit of velocity and a unit of energy in both of these buckets, so a unit of velocity would be like 1 mile per hour. And there would be some corresponding unit of energy for that 1 mile per hour. Well, if we doubled the speed, look what happens to the kinetic energy. It increases by a factor of 4. And if we remember, energy describes, in a sense, the amount of work that you can get out of that energy. One can say that to double an object's speed requires 4 times as much work or 4 times as much effort. Likewise, increasing it 3 times, so just simply going from 1 mile per hour to 3 miles per hour, takes 9 times the amount of energy, or it would take 9 times the amount of work to speed it up to a very specific speed. And as we increase, we see this relationship is a squared relationship. So 6 times 6 is 36. 7 times 7 is 49. 8 times 8 is 64. And we get up to 10, and we see that to go from 1 mile per hour to 10 miles per hour requires 100 times more energy, or 100 times more work to do that. So this can also be seen in a completely different light. We say, well, we get 100 more units of energy by increasing our speed, but it also takes 100 units of energy to go this speed. So another way to represent this very same thing is with a graph. So if we have velocity on the left, kinetic energy on the right, we see that these two things are not the same height. They don't grow the same. So this little bit of velocity will give us this much kinetic energy, or it will take this much kinetic energy to produce this little amount of velocity. So traveling at really fast speeds requires a lot of energy. Now, let us talk about some implications of this. So imagine you have this ball and it's at a specific height, this height. If we were to drop this ball, right before it hits the ground, it would have a very specific speed. So a height gives us this speed. So one would ask, how high would we have to drop the ball so that right before the ball hits the ground, it's moving twice as fast than it's moving right before it hits the ground here? So this is always a fun question to ask to students. And the most common response is, well, you double its height. If you want it to go twice as fast, just drop it twice as high. But in this situation, by doubling its height, all we have really done is double the amount of energy that was in the ball. So this doubles the energy, but it does not double the speed. Why doesn't it double the speed? Because to double the speed, we need to quadruple the amount of energy in the ball. And the only way to do that is to lift the ball 4 times as high. So if we were to drop the ball 4 times higher, this would give us twice the speed. Now, another implication of this is with vehicles. So here we have 2 cars. Imagine the top car is traveling 20 miles per hour and the bottom car is traveling 40 miles per hour. So the bottom car is traveling twice as fast. Now, the thing when it comes to cars is that when you slam on the brakes, they can only dissipate energy at a certain rate. So if the car on the top can stop in this amount of distance, then the bottom car, because it has 4 times the amount of energy, must stop 4 times farther. So the car traveling twice the speed takes 4 times the distance to stop. Likewise, if it was traveling instead of 40 miles per hour, let's say it's traveling 80 miles per hour, this means it would take 16 times the distance to stop. So this is a big reason why we have the speed limits at the limits that we do, because as it turns out, the faster and faster you are traveling, the harder and harder it is to stop at a certain distance. And this is this is a really awesome concept to bring up to students, because one fun engagement question to ask is to pose this question. So imagine you have a car that is traveling 20 miles per hour and traveling 40 miles per hour, and they're the exact same mass, so they're the exact same car. How much more damage will a car traveling 40 miles per hour do if it crashed into something than the car traveling 20 miles per hour? One would think it's traveling twice as fast, so it's going to cause twice the amount of damage. But if we remember that the energy involved, we'll immediately see that the car traveling twice as fast will cause 4 times the amount of damage. And if it's traveling any faster, it just increases according to the square of the velocity. Another fun way to engage students and getting them thinking about this concept between kinetic energy and velocity is going back to the classic bigger and slower versus smaller and faster problem. So I brought this problem up when we were talking about momentum. The engagement question was, if you were playing football and you could choose, would you rather be hit by the big and slow person or the small and fast runner? Which one would you choose? And I don't know why it is, but it seems to be that for whatever reason, when students really think about this question, they always assume it's the big guy that's going to do the most damage, because he's so big and so massive. We think it's the big things that do the most damage. If someone has a big fat fist, it's going to do more damage than a tiny little fast fist. So for argument's sake, let's imagine both of these two guys are carrying the same momentum. So what this guy lacks in speed, he gains in size. And what this guy lacks in size, he gains in speed. So if we look at these guys individually, we'll say that he has more mass. So that gives him more mass. But he has the same momentum, which means that the most he can do is transfer the exact same amount of momentum as the small guy. But it also means he must be moving slower. So it means how does that compare to velocity? We know that the faster things are moving, the more that affects kinetic energy. So as it turns out, this bigger guy will not have as much kinetic energy. If we look at the little guy, we see that he has more velocity. And remember, velocity affects energy much more than mass. So this means he will always have more energy. So we could say the faster object will always do the most damage. So this is amazing. If you're trying out for football and you have the ability to either increase your speed or increase your mass, you always want the ability to increase your speed, because it has a much more dramatic effect on your energy, even though it may not have a huge dramatic effect on your momentum. So let us look at an example that kind of illustrates this point. So here we have this cannon, and after it fires a cannonball, we learn from our study in momentum that if we compare the momentum of these two objects, we will see that the momentum of the cannon is actually equal to the momentum of the cannonball. So this is a real life application of two objects, that this is big and slow and this is fast and small. So what this guy lacks in speed, he makes up for in mass, and what this guy lacks in mass, he makes up for in speed. So they have the exact same momentum according to the conservation of momentum. But a simple question would be to ask, would you rather stand on this side of the cannon, or would you rather be over here in front of the cannonball? And I think the obvious answer to that question is always we would rather be behind the cannon, because cannonballs are meant to do one thing, and that is to destroy. And the reason it can destroy is because if you compare the kinetic energy of these two objects, they are absolutely not equal. The kinetic energy of this ball would probably be much higher than the kinetic energy of the cannon. And in that case, we want to be behind the thing that is less energetic. So when it comes to energy, whether that be kinetic energy, potential energy, thermal energy, it's always important for students to recognize that energy describes matter's ability to do work. So stress this to your students, that when they think of energy, they should immediately associate energy with work. One big common misconception that students can have is that they associate energy with force, and it should be associated with work. And work, again, describes the effort involved in either speeding something up, slowing it down, or moving it against a force. So energy should always be looked at into how much work can something do. So if we have this hammer and we nail, and then it comes slamming down on this nail, it's actually the kinetic energy of the hammer that drives the nail into the piece of wood. Here is another good example of kinetic energy. So here we have this car, and let's imagine the car is not really moving, but it's free to roll. It starts off with a high amount of potential energy because it's at a certain height, but it has low kinetic energy because it's not moving. And as it moves down the hill, it finally reaches the bottom, and with that point, it has a low potential energy because it just lost all of that potential energy. But now it has high kinetic energy. But now it faces this uphill battle, so it will require work to get up that hill. And as we said, potential energy is not going to help this car out because all of that was used up as it fell. So it's now this kinetic energy that will help the car accomplish the work to get up the hill. So when we look at this type of example, we immediately see that there is this close-knit relationship between potential and kinetic energy. One transfers into the other, which transfers into the other, and so on and so forth. One common thing students will do, which is kind of, I guess, not really a good thing, is that they will see this binary system to where the car either has potential energy or it either has kinetic energy. So, for example, it was either at the top of the hill with lots of potential and no kinetic, or at the bottom with lots of kinetic and no potential. But whenever an object is really accelerating, it has a combination of both potential and kinetic energy. And this is something that we can always keep in mind. And one thing that will help is to always change our verbiage whenever we ask specific questions. So instead of saying, what type of energy does this car have, saying, what are all the types of energy that is in this car at very specific moments in time? And pick moments in time, not when it's just at the top of the hill or when it's at the bottom of the hill, but what about when it's in the middle of the hill right here? How much kinetic energy does it have? How much potential energy does it have? Does it have more potential than kinetic at certain points? And how does these values change? Because as the car moves down this hill, these values change. And we see this really clearly in this example of the pendulum. So if we take this pendulum and it starts rocking back and forth, and we're interested in what is going on with the potential and kinetic energy of this pendulum, we'll immediately notice that if we could visualize these energies, that they're constantly changing. So when the pendulum is at its highest points, it maxes out its potential energy. When it's at its lowest point, it's maxed out its kinetic energy. But in all the individual or on intermediate points, there's some combination of both. So one can say that at any point in time, it has a certain amount of potential and a certain amount of kinetic energy. What if we were to add these two energies together and figure out what at any point in time is its total potential and kinetic energy? And that will give us the total amount of energy. Notice the total amount of energy does not change. This is what we mean by the conservation of energy. We mean that this energy does not increase and it does not decrease. So if we can account for the potential energy, the kinetic energy, and add those two together, we get the total energy. Now this is not a real pendulum. If you swing a real pendulum, given enough time, it'll slowly die down and stop swinging. So it seems as though that energy was lost. So in order to paint a complete picture of all the energy, we would have to bring in one more that describe the thermal energy. So if we can account for all the thermal energy, all the potential energy, and all the kinetic energy, then no matter what happened, that energy would always remain the same. Energy would always be conserved. So this total energy is called the total mechanical energy of the system. So the big question is, where does this energy come from? Well, imagine we have this pendulum and we do work on the pendulum by pushing it up. So before this pendulum is released, all of the energy is stored as potential energy. And as it drops and it swings, it will be converted into kinetic energy. So this actually gives us a different way of looking at the motion of objects. One thing it's easy to do is to take these energy concepts and take Newton's laws and say they're two different things. But in fact, they're two different ways of looking at the exact same thing, and that same thing is motion itself. See, we can look at this pendulum and we can use Newton's second law to analyze all the forces acting on it, and then we can figure out what the speed and acceleration of this pendulum is at any point in time. Or we can look at this pendulum and say, what is its potential energy and kinetic energy at any point in time, and use these values to figure out the velocity and the motion of the pendulum. So if we let that go, we will see that this potential energy and kinetic energy bounce back and forth, but the total energy remains the same. So one really neat demonstration that you can use to get your students to really think about the conservation of energy is you take a ball, a tennis ball or some type of ball, and hold it out in front of you and ask your students, if I drop the ball, will the ball bounce up back to its original height? And by experience, most students will say, no, it will not. So you'll drop it and you'll see that it does not bounce back up to the same height. And then the question becomes, what happened to the energy? And it'll get them thinking about this potential and kinetic energy and the total energy that was originally in the ball. So with enough thought, they may think, well, that energy must have gone somewhere. And this is the right train of thinking, that the energy doesn't just disappear out of existence, it goes somewhere. And as it turns out, that energy goes and becomes some type of thermal energy. But after they've come to that conclusion, take the exact same ball and this time have a little plastic cup filled with some water and place the ball on top of that water and drop the cup and the water together. And right before you drop it, ask them the same question. Should the ball bounce back up to your hand? And as it turns out, if the ball is elastic enough, most balls that are balls made to be balanced are elastic enough. So if you drop it, and I guess I would recommend trying a few balls first to make sure it will bounce correctly. But if you drop it, it will actually hit your hand, or it will bounce up higher than your hand. And this is a really fun exercise because it seems totally counterintuitive, because you supply it with a certain amount of energy and then you drop it, and it seems as though the ball was able to bounce up higher than your hand. How is that possible in light of the conservation of energy? And these type of activities are really, really good activities to help students think critically about transformations of energy, where energy comes from, and how it's transferred. So really good activity to get them to critically think, because it seems counterintuitive. All right, so this is about all I have about topics of kinetic energy. So now I want to open it up to any questions. So if you have the chat box open, you can type in your question right now and we will discuss these questions. All right, so I see no one is typing in any questions, so I'm going to assume there weren't any questions. Next time, we are going to be talking about thermal energy. So the last few lessons found in Energy 1. This webinar will be on February 4th, 2016, and we will start at the exact same time, 4:30 Mountain Standard Time. So as always, you can find the recording of this webinar on both the Physics Lab and the See the Change USA Edmodo page, and you will also be able to find the PowerPoint that we just covered on the See the Change USA Edmodo page. And just to show you how you can become a member of the See the Change USA group if you are not already a member, I'm going to change my share screen. I'm going to pull up the internet. And forgot to have this loaded. I was going to have this all loaded. But I'm going into the physics lab right now. You can access it right from the physics lab. So from the physics lab, there is this button right here that says resources. Click on resources, and then you'll see a tab that says links. Go ahead and click on links. And then here is the link to the See the Change USA Edmodo account. So view that, and it will take you to this link. All right, so it'll take you to this page right here. If you do not have an Edmodo account, you can create a free account by clicking on I'm a Teacher, and all you need is an email address and a password. I accidentally clicked when I should not have, but it's still here. Email and a password, and then you can get a free account. I already have an account, so I'm just going to log in. Oh, this is why. So, and after you create the account and log in, you will get this page, which is a join request page. Since I'm already a part of the See the Change USA group, it says you're already a member. But if I wasn't a member, there would be a little button right here that says send a join request. So go ahead and send a join request. And then within about 24 hours, you will be accepted and you will be given access to the different small groups, which have all the materials that you'll have a bunch of different materials at your hand. So that's how you can be a part of the group, and that's where these PowerPoints will be posted. So now I'm going to go back to previous share. All right, so that's how you can get access to the Edmodo group. So for additional teacher content training and support, you can always go to the physics lab. Inside the physics lab, there's the teacher content training. Inside those, we've made many videos, so you can watch those videos and get training that way. Any of the past webinars that we've posted, you'll also be given access. You can also find those webinars made. Also, you can go into the See the Change USA Edmodo group, and this is a really awesome place to collaborate with all the teachers that are on that group. We have all the teachers working through, so you'll be able to post questions and not only access the See the Change USA staff, but you will have access to all of these teachers and the wealth of information that everyone carries. So really great place to post questions, get ideas, or anything like this. Or you can always send me an email at vincent.weiss@seethechangeusa.org. If you're struggling with specific concepts in physics and would like one-on-one training, do feel free to send me an email, or you can send Laura an email, laura.horvath@seethechangeusa.org, and we'll be able to schedule a one-on-one session with you, and we can work through whatever we need to work through. Or do feel free to give us a call at 1-888-843-0671. All right, and if there are no other questions, then I just want to thank you all for time, and we are really excited to see you next time. All right, thank you so much.